What is statistics? The art of gathering, analyzing, and making conclusions from data, which basically means first you search for information and then you find out what it means. This definition is important because everything we talk about during this presentation relates back to it. When it comes to stats, nothing of too much importance happened until the late 19th and early 20th century. Around that time, Francis Garland and Carl Pearson started to forge its modern definition by making inferences from data with their work. Most importantly, they were able to introduce the ideas of standard deviation, correlation, and correlation coefficient. Later on, in 1915, R.A. Fisher started to try and use small samples of a population in order to represent the population as a whole. Then, in 1928, Jerzy Newman and Egon Pearson started the trend of using their surveys to obtain information from a small number of people in order to represent the larger group. Like I said before, statistics is just a person trying to figure out what to make of a bunch of information. So from there, let's look at a few practical uses. First, in elections, and then in experiments. This year in the presidential election, every news station had a different poll predicting a different percentage of votes to each candidate. But how are these polls made? To try and see who was leading the presidential election, what polling studies did was ask a random group of people, call it a random sample, who they were voting for. Let's say they asked a random 3,000 people. Let's say 1,623 of those people said they'll be voting for Barack Obama, and 1,377 said they'll be voting for Mitt Romney. You can't just assume that those 3,000 people perfectly represent the population. That group might contain a higher percentage of Democrats and Republicans than the total population does. So in order to fix this problem, statisticians started to use margin of error and confidence intervals. To solve this problem, you must do a few things. First, write down a statement just like this one. We are blank percent confident that between blank and blank number of people will vote for Barack Obama. The rest of the problem is just filling in those blanks from the statement we just made. The first blank is easy, just pick a number. Decide what confidence level you want to use. Some of the more common ones to use are 90, 95, 98, and 99%. In this case, the decision is totally yours. How confident you want to be that the actual percentage of votes for Barack Obama will fit into the range you present is what we're looking for here. If you want to be 90% confident, go with 90. But if you want to be as confident as possible, then pick 99%. The goal of confidence intervals is to present a range based on how confident you want to be that the whole population will fit into the range you present. So, the greater the level, the greater the range. Which makes sense because the more confident you are, there has to be more values that could possibly go into this range. So if I've got a range of 10%, it's very likely that the observed value is going to fit into that percent. So it's going to be a higher level of confidence. Whereas if I present a range of like 2%, it's going to be a much lower level of confidence because I cannot be nearly as confident that the observed value, how many votes each candidate will get, will fit into this range that we will be coming up with. In this case, we will pick a 95% confidence level because it's a fairly high level of confidence, but keeps the range pretty low. The higher level of confidence you pick, the greater the range between your two percentages. So I didn't pick a 99% because I didn't want such a large range that we couldn't really get any data out of it. As of right now, we can fill in one of our three blanks. We are 95% confident that between blank and blank percent of people will vote for Barack Obama. Now we just have two more blanks to go, which will be our range. To find the next two blanks, we must find the margin of error, or how much larger or smaller the real percentage of people voting for President Obama is than the observed percentage from our survey. We do this by plugging numbers into the following statistic. And I know when you see that statistic, it's pretty intimidating. When you break it down into what these things actually mean, it's not too bad. So E is the margin of error, it's what we're calculating. Z with the subscript is a critical value, which is a constant for a confidence level of 95%. That's 1.96. P is a ratio of people voting for President Obama to the total sample from our survey, which was 54.1%. Q is the ratio of people voting for Mitt Romney to the total sample, and that's again from our survey, which is 45.9%. And N is the total sample size. When you plug in the actual values into the statistic, you get 1.8% for your margin of error. Since the observed percentage of votes for Barack Obama in our survey was 54.1%, you both add and subtract 1.8% to find two values. When you add 1.8%, you get 55.9%, which is the highest percentage of people, based on our survey and the confidence level we're working with, that could vote for President Obama. Then, When you subtract 1.8%, you get 52.3%, which is the lowest level that could vote for President Obama based on the 95% confidence level and the survey we used. Congratulations, we've now filled in all three blanks, and we now know that we can be 95% confident that between 52%, 52.3%, and 55.9% of the people will vote for President Obama based on the survey and a 95% confidence level. Again, going back to the original definition, we are trying to find out what the data means. A great example of this is experiments. Any of you who have taken or are taking AP Psych or Special Aspects will be using some sort of test to see if the data given in your experiment matters or not. Let's say you design an experiment to test if gender affects education choices. You basically are looking for, are they independent, or is there a correlation between the two? Just like in any experiment, you start by making two hypotheses, a null and an alternative. Null being that gender and education are independent and have no correlation. The alternative being that gender and education are not independent and they are correlated. So again, we're going to need to get some data. Let's say we ask 1,000 people, 550 of them being male, 450 of them being female. We ask them if they have no degree, a high school diploma, or college education. And then with this information, we'll make a table like what we see here. Then what we have to do is make another table, this one with expected values. And expected values are how many males or females would have each type of education if the values were evenly distributed. So if there are 310 people with no degrees, how many of them would be male and how many of them would be female based on the ratio of male to females that were asked to do this in the experiment. So mathematically, this is expected values equal to row total over the total multiplied by the column total. This must be done 6 separate times to get all expected values. Once you create your new table with expected values, this is what it should look like. Next, what we're going to do is take the observed value, subtract it by the expected value, square that number, and divide by the expected value. Do this for all 6 of the values and add it together. The result we will look at on a table in the next few slides. Here comes the analysis part. After all that math, you have a number, 0.4798. Then what you need to do is find what's called the degrees of freedom, which is the number of rows minus 1 times the number of columns minus 1. In this case, it's 3 minus 1 times 2 minus 1, which is 2. Then what you need to do is take that number, 0.4798, and the degrees of freedom, 2, and find it on the following chart. The first thing that needs to be done is looking at 2 degrees of freedom, which is what we found out that our degrees of freedom were for this problem. Now, if you look to the top of the headings, the probability is decreasing as the numbers increase. And since 0.4798 is smaller than 1.38, we see that the probability of this, the p-value, the probability of this this result coming from chance is higher than 0.5. So the probability that this result came of chance is higher than 50%, meaning that our results are in no way statistically significant. Thank you.